Alright, so let's go ahead and solve a problem now that we've watched the videos on 3.1 and 3.2. So we've got the molar analysis of a gas mixture at 30 degrees Celsius, 2 bar is yada yada yada, and we want to know the mass fractions, the partial pressures, and the volume if we've got 10 kilograms of the mixture. So let's see what we're given. So we are given, it says the molar analysis is, and then it gives us these percentages, so it's the mole fraction. So you got 0.4, 0.5, and 0.1 for all of those components. You get nitrogen, CO2, and methane, CH4. And then you know the temperature, so that's the temperature of the mixture, which if we're using Dalton's model, we're going to say that that's the same temperature as the components. And then we're also given the pressure. The pressure is 2 bar or 200 kilopascals, if we want to put it that way. And the things that we want to find all of these things. So the mass fractions, the partial pressures, and the volume if the mass is 10 the mass of the mixture is 10 kilograms. And as far as assumptions, I don't know, maybe I don't really need to make any assumptions, so I'm not going to make any until I think that I actually have to. So let's see if we can just solve it without any simplifications. A lot of times a table is really useful for just keeping your information organized. So in the first column, what you're going to put is the component, and you've got 3 components. So there we go. The next column, you're going to put your mass, and I've put what my units are, so I don't have to write my units over and over and over again. I don't actually have my mass. I don't really have any information about mass, so I'm just going to skip that, and I'm going to come back to it. The next column is your molar mass, and those values you can look up for your components. So you can look those up in table A1, or if you were in English units, A1E. So I've got molar mass for nitrogen, CO2, and methane. They're all in there in table A1. So let's go to my next column, and that's my number of moles. So you can see that the mass and the molar mass are both related. If I divide the mass by the molar mass, I get the number of moles. I actually don't know the number of moles, so I'm going to kind of skip that, and let's go see what else I've got. So the next column I've got is my mole fraction. That I do have. So I've got those numbers. I'm going to go ahead and plug those in. And now what I'm going to do is I'm going to solve for the number of moles of each component by not guessing, but just putting in a really convenient value for the total number of moles for that denominator in the mole fraction equation. And a really convenient value would be 1 kilomole. So it doesn't mean that we have 1 kilomole, but the thing is, part A and part B specifically aren't really things that depend on how much or how big our mixture is. It depends on the ratios of all things. So it doesn't really matter what I use to calculate, what number for the total number of moles I use to calculate the mass fraction. It's just a ratio. So I'm just going to use 1 kilomole, and that would give me 0.4 kilomoles of nitrogen per kilomole of mixture. And then if I go through and I do the math for the other guys, I've got 0.5 and 0.1. So my math was just really, really simple. I just multiply 1 kilomole times the mole fraction, and that was it. And now I've got some information that's going to allow me to calculate the mass. So the mass of my nitrogen, it's going to be the number of moles, so that's in my fourth column, times the molar mass, which is in the third column. So 0.4 times 28.01, got 11.201. 0.5 times 44.01, there we go. 0.1 times 16.04, there we go. So I only have one more column that I got to fill in, and that's what I'm actually after. It's my mass fraction. So my mass fraction, well, let's see. I do need to know the total number, or the total mass in my mixture, so that's fine. I just add everything up. So I've got 34.813 kilograms, and that's per kilomole of mixture as I've calculated it here. So in effect, what I've calculated is the molar mass in my mixture, but we'll come back to that in a second. So my mass fraction, I've got 11.204 divided by 34.813. There we go. And so on and so forth. 22.005 divided by 34.813. 1.604 divided by 34.813. And now I've filled in all the information, and I've got my mass fraction. So there are my mass fractions. I've put some units on here. A lot of times I just drop those, but I'm going to leave them here because sometimes it's useful just to see where those units cancel out as you're doing calculations with them. All right, so part B, I need to know the partial pressure. And when you watched the video for 3.2, we talked about Dalton's model, and then we also talked about how we can use the ideal gas law to get a relationship between the mole fraction and the partial pressure and the overall mixture pressure. So that's what I'm going to do here. And I've got all those numbers. My pressure is 2 bar, my mole fraction, well, I'm given that information. So I just plug in the numbers and I get my partial pressure for all 3 components. Super easy. Making the assumption that everything behaves as an ideal gas, it's not really a stretch. So you could go through, you could look at the critical temperatures for nitrogen, CO2, and methane and see if at that temperature and pressure do you have an ideal gas? I'm not going to make you go through that song and dance every single time. You can go ahead and make the assumption for all the gas mixtures that we're going to talk about in this class. You can go ahead and assume that they behave as ideal gases. All right, part C. So I'm supposed to find the volume occupied by 10 kilograms of the mixture. So I'm going to use my ideal gas law. So I know my mass. That's great, that's 10 kilograms. I know my pressure, that's 2 bar. I know my temperature, that's 303. And remember, I'm applying this to the mixture. I'm keeping track of that. So that R is the specific gas constant for my mixture. And of course, I don't have that tabulated anywhere. This is a random mixture of gases, so I have to calculate it. And this is related by R bar over my molar mass. Once again, that molar mass is critical to being able to go between things on a per mass basis and a per mole basis. So my R bar value, I've got that, and then my molar mass of my mixture, I need to calculate that based on the mole fraction of each component times the molar mass for each component and sum all of those up. So there we go. There's all my molar masses, all my mole fractions, my universal gas constant, and when I calculate everything, what I get is 0.238819 kilojoules per kilogram K. Now, just a side note, the denominator of that big long equation right there, that was my molar mass of my mixture. If you calculated that up, you would get the when we had our table, we summed up all of the masses, and the sum of all those masses was based on 1 kilomole of mixture. So the number, I think it was 34 point something, that is your molar mass. You have 34 point something kilograms per kilomole of mixture. So, but anyway, we went ahead and calculated it, and I think I have everything I need to plug in and calculate my volume. So, all right, well, I hope that was helpful. Thank you for watching.